next slide. All right, now let's get into a couple of other reactions of aldehydes, and aldehydes in particular. The Tollens reagent. This is a beauty. It's a difficult test. Everything has to kind of be right. You have to kind of practice this and to get it right. The glassware has to be really clean. But you could take an aldehyde and a Tollens reagent, which is a silver ammonia complex, in a basic solution, and it will oxidize the aldehyde to a carboxyl group. The ammonium salt of that carboxyl group. The key thing is that this silver, which is a +1 silver, becomes silver, metallic silver, and it will silver the inside of the flask, turn it into a mirror. That's actually what will happen. The glass has to be really clean. The glassware has to be clean. It has to be very basic. This complex has to be made nicely. But it is a test for indicating that, oh, we've got an aldehyde here. Those of you in the 1107 lab, eventually we're going to have the organofunctional group test experiment, where you are given an unknown and you do a bunch of tests on it and try to decide, is this an alcohol, is it an aldehyde, is it an alkene, what is it? And so there are these different tests you can do. If you did this test and got a mirror, it would point to the fact that your unknown is an aldehyde. All right, there isn't anything else that will do that. Alcohol won't do that. Why? Because the aldehyde is being oxidized and the silver is being reduced. +1 goes down to 0. That's reduction. This is an aldehyde. It's going to a carboxyl group. That's oxidation. Okay, so that's a Tollens test. Another test that is quite, see that I wrote there, start here. That's where we started. Another test that is really appropriate in the health, allied health region is this one here. This is kind of presenting it as another test for aldehydes, but it's a particular kind of aldehyde. It's an aldehyde where the next carbon over has a hydroxyl group on it, and you get, which happens to be glucose. Now we'll get into this in chapter 16. So let me just put a note. You'll see this slide again in chapter 16 when we talk about saccharides, carbohydrates. We'll get into this. And glucose is a monosaccharide. It's an aldehyde functional monosaccharide. It's got an aldehyde group on the end. Sugars are very soluble in water. Why? Because there's OH groups on all these carbons. Just from the homework you just recently handed in, where the molecule had 4 hydroxyl groups. And that was the molecule that was more soluble in water. Well, here's a molecule that has only 6 carbons and 5 of them have hydroxyl groups on them. So sugar, it's floating around in your bloodstream. In an aqueous environment, it's very soluble. Well, here's the relevant thing I'm saying here. You got an aldehyde. This is Benedict's reagent. You'll see this a little bit more in the next slide. It's blue. It's copper in the +2 oxidation state is blue. So if you mix Benedict's reagent with glucose, the copper will oxidize this aldehyde to a carboxyl group, and it will reduce the copper from a +2 to a +1. When the oxidation state goes down, that's reduction. And the beauty of that is that copper is different color. Copper plus 2 is blue. Copper plus 1 is red. So it changes colors. And that color change tells you that you were in the presence of an aldehyde like this. Okay, how do they use this in the clinical arena? Well, if someone is passing glucose in their urine, which is not a normal condition, if you're actually excreting glucose because of high glucose levels or diabetic condition of some sort, you could detect it real easily by this Benedict's test. Here's what it would kind of look like. So if you had, here's the Benedict's reagent. It's a copper sulfate or copper nitrate solution, but it's copper in the plus 2 state. So it might be copper, any copper plus 2. So the plus 2 ion here is going to be blue. And what we've got here, let me label these test tubes. Left panel, solutions with 0.5% glucose and 2%. So let's label those. Here's our 0.5%. And here's our 2% glucose. So this test tube here has 4 times as much glucose in it as this one. So we're going to take that Benedict's reagent, put half of it in this test tube and half of it in that test tube. And here's the results. A little bit of Benedict's reagent left, but everything poured into there. Little bit of glucose here, reduced a little bit of the copper. So we've got some blue and red mixed together, forming a green, forming the green color. All right, well, so you do see a color change, but it hasn't reduced all the copper. So you don't get as vivid a color change as with the 2% solution. So here's our 0.5% with Benedict's, and here's our 2%. Follow that? This is a test, and it's a real easy test. I mean, this is something you can buy a test kit at Walmart or at Walgreens, I would think. I haven't tried to do that, but I bet you could. You could walk into a doctor's office, and rather than say you need to go to the hospital, we need that, they can test it right there. They take a urine sample, and what they might have is a little kit with these little sticks on it. They dip it down into the urine sample, and it changes colors. The thing changes colors, or it doesn't. Doesn't change colors? Negative. No glucose in the urine. Changes colors? Positive. There's glucose. This person is secreting glucose.
I think I got lost when you were explaining the percentages of glucose.
Okay. Okay, now notice 0.5%. 2% is 4 times as concentrated. Okay? 4 times 0.5 would be 2. So this is, there's 4 times as much glucose here as there is here. All right? So, but there is glucose. There's glucose here. Glucose in both test tubes. But there's a lot more here, 4 times more. So the glucose that is here is reacting with that Benedict's reagent, but not all of it. Only some of it. And so now we've got some red, and then we have some of the copper that's still blue mixed together, forming a green color. All right, that's why that's turning out green. There's no copper that's green. It's either blue or red, but a mixture of the two isn't giving us blue or red, it's giving us green. So actually, even the color change could actually indicate a little bit whether there's a lot of glucose present or not so much. If it all turns red, you know, there's a lot of glucose. Well, yeah, the Statue of Liberty is, I think, made of copper, and it's forming. It turns green. It does turn green. And it forms, I guess, copper oxide. It's forming. It's being oxidized by the air, or it might be forming acid rain on there. It could be forming copper sulfate or something. But that is copper metal now being oxidized to copper something, copper chloride, copper sulfate, copper oxide, because they're starting out with metallic copper.
Is it different?
Yeah, these are none of this is metallic copper. See, this is not. This would be like copper nitrate. I'm not writing the nitrate. I'm saying that what is blue here is this copper ion. That's what's blue. And this is forming copper oxide. And what is red here is the copper +1 ion. Okay? But what Statue of Liberty would have been covered with copper, and then it's reacting with something and maybe forming copper oxide. Yeah, so there's copper, but it's not this reaction per se. Okay, so that's the Benedict's test. And again, in 1107, I think when we do the aldehydes, study the aldehydes, we'll do this test. And also when we look at sugars, we'll do this test. Okay, and this is what I was just saying a minute ago. Oxidation in this direction, reduction in that direction. More oxygen, less hydrogen. More hydrogen, less oxygen, to go in the reverse direction. So reduction. More hydrogen. Well, whenever you hydrogenate something, you are reducing it. This is reduction. Reduction of carbonyls. And a primary, or an aldehyde. An aldehyde is going to produce primary alcohol. And this is a ketone. And when you hydrogenate it, it's going to produce a secondary alcohol. Okay, so what you're looking at here are two reactions. Yeah, this is kind of a busy slide. I know that could throw you. This isn't just one reaction. Here's one reaction with, what are you doing? You're hydrogenating a ketone. Here's the other reaction. What are you doing? You're hydrogenating an aldehyde. Follow me? I'm just not writing that twice. So there are two reactions here. So let's just tease one of them out. This top one. No, the bottom one. So right here, you got the aldehyde. There's your aldehyde. Oh, it's 4 carbons long. Let's put another carbon over there. There's your aldehyde. And we're reacting hydrogen with it. And there's let's say a platinum catalyst. That's my favorite. We're adding hydrogen to that bond. And we're going to get an OH there, and we're going to get another hydrogen there. Here's our hydrogen. If you want to see the two separately, we could just kind of push this one down here. So let's say it started this way. Now we're going to add a hydrogen there and a hydrogen there. hydrogenating a carbon-oxygen double bond, and we get a primary alcohol. So an aldehyde goes to a primary alcohol. All right, this should make sense. Keep thinking this in mind. The oxygen is on the end. The hydroxyl group is going to end up on the end, which is a primary alcohol. All right, and so the top reaction is taking a ketone, and this is butanol. This is butanol here, and it's going to form 1-butanol. Right? And the top one is butanone. It's a ketone. So we're going to take butanone plus hydrogen with a platinum catalyst, and we're going to get, now notice here the hydroxyl ends up right where the oxygen started out. And there's our other hydrogen. And we get 2-butanol. So butanone plus hydrogen yields 2-butanol. And in general, a ketone, the hydrogenation of a ketone forms a secondary alcohol. Okay, that's the important thing to learn here under the category of reactions of aldehydes and ketones. They can undergo reduction. Any questions? Okay. After an exam and after lunch, this is not the best reaction to be talking about. Hemiacetal. Let's get our minds wrapped around just the prefix, hemiacetal. The Earth is divided into two what? Two hemispheres. The Earth is a sphere. A hemisphere is half of a sphere. Half. Okay, now look how smart you are. Now you know that a hemiacetal is half of an acetal. So if anybody asks you, what is a hemiacetal? Just say it's half of an acetal. Of course, it begs the next question. What's an acetal? And we're not going to worry about what an acetal is. We're going to worry more about a hemiacetal than we are an acetal. But if you take, we just added hydrogen across a carbon-oxygen double bond. Now we're going to add a hydroxyl across a carbon-oxygen double bond, and we're going to form a hemiacetal. So let me compare those two. We had our little situation here. We have a hydrogen. We added across the double bond. So what did we get? A hydrogen went on the oxygen, and a hydrogen went on the carbon. Right? Okay, now let's look at this. Let's take a carbon-oxygen double bond, and in this case, we're going to react an OH. We're going to add an OH across that bond. A hydroxyl that's on a carbon, an alcohol. This is almost any alcohol right here. Okay? you should be able to draw what this would look like. What are we going to get here? An OH. An OH. That H is going to add on to there. So that bond is going to break, and we're going to get that there. Where is this going to go? It's going to go right there. We're going to get an ether. What did we have here? We had a hydroxyl group, and now we have lost the H to that oxygen, and the rest of the molecule went on the carbon. And this is a hemiacetal. Okay, let's get a real world example. Let's take a molecule here, simple one. Acetaldehyde. Or ethanol. Plus ethanol. Okay, now that looks a little strange to you because we usually just write these like this. Something like that, but I'm exaggerating this. I'm focusing on this hydrogen-oxygen bond because that's the bond that's going to disappear. And the hydrogen's going to go here, and the rest of that is going to go there. All right, so now I'm going to write the product over here. We're going to bring this over here now. We've got a carbon. All right. This hydrogen is going to go there. And the rest of this molecule is going to go right here. I've told you all the bad news. Now the good news. You don't need to name this. All right? You just need to predict the product of an alcohol reacting with an aldehyde. And that's where this acetal is coming, or acetal. I guess it's from the acetal. This is the aldehyde. So an alcohol reacting with an aldehyde gives you a hemiacetal. All right, your chapter 13 homework has I might have just did it for you. Not sure. It's a simple aldehyde, a simple alcohol, and it says finish this hemiacetal reaction. I think it's it's not your last question, but it's one of your questions.
Is this an ether or is this
well, we got an ether linkage right there. No, this would be called a hemiacetal. You got an ether with a hydroxyl next to it.
Is that how you'll tell the difference?
Yeah, just a regular ether would just, wouldn't have that hydroxyl there. Okay. There is also such a thing as a hemiketal. It's not much different, where you would take a ketone. I'll leave this hemiacetal right there. Just imagine we just had this ketone. Instead of a hydrogen down here, we had a carbon. And we did the same thing, same alcohol. Ethanol. And now instead of ethanol over here, we have acetone or propanone And if we added an alcohol across that, what's wrong with that?
You got the O and the
Right. Right? See what's wrong with that? Oxygen is here, and the hydrogen is up there. All right. Sorry. I think first day I said, write in pencil. Thinking you might make some mistakes, but you got to write in pencil to cover my mistakes. Okay, yeah, I wanted to put the same molecules we got up there. Hydrogen is going to go here, the rest of the molecule is going to go there. So what would that look like? It would look like this. And where this above us is a hemiacetal, I guess I already wrote that up above there. This is a hemiketal. And how is it a hemiketal? You've got the reaction of an alcohol with a ketone, giving you a hemiketal. So an alcohol plus a ketone gives you hemiketal. Alcohol plus an aldehyde gives you a hemiacetal. There's 2 or 3 slides here that are just basically all just taking another look at this. There's your aldehyde plus an alcohol forming a hemiacetal. That's the general structure of it. This is kind of showing what's going on. Here's methanol. That hydrogen was here, and all they're saying that this hydrogen on methanol goes up on the oxygen, and this goes up here, and you got your hemiacetal. Same reaction can take place on ketones to form the hemiketal. All right. Typically at the end of the book, at the end of each chapter in the book, there is a reaction summary like this. Just summarizes all the reactions. There is another one that looks like this, which is probably the best one to look at. So an aldehyde, that's a double bond up there. It's kind of hard to see. Carbon-oxygen double bond oxidizes to carboxylic acid. An aldehyde plus hydrogen forms a primary alcohol. A ketone plus hydrogen forms a secondary alcohol. Be aware of this. A ketone plus alcohol is a hemiketal. Aldehyde plus alcohol is hemiacetal. You don't have to take it over here to the actual ketal or acetal, where it reacts with another molecule of alcohol. So just kind of to here. And don't worry about these. The tautomerization, the aldol condensation, we're not going to include those in our reactions. I think what we did forget here, what's not on here, might be over here. If we took a primary alcohol and oxidize it, what do we get? We get an aldehyde. We take a secondary alcohol and oxidize it. We get a ketone. Yeah, I think, yeah. That's how you would prepare an aldehyde or a ketone. And then there's the reactions of them. I think that's it. That's chapter 13. Let me just save that, and we'll go on to chapter 14. So, stretch your legs.